Hello and welcome to The Explainer. Okay, let's dive into this because today we are taking an absolutely incredible journey into the underlying architecture of reality itself. We're going to unpack a brilliant source text that fundamentally challenges how we conceptualize, well, kind of everything, from the intricate biology of our own bodies all the way to the core physics governing the cosmos. It's all about the synthesis of complexity and how we might, just maybe, finally crack reality's deepest, most elusive code.
To kick things off, I want you to take a quick second and just look at your hands. Seriously. Now, take a glance around the room you're sitting in. Every single complex system you're interacting with right now, and yeah, that includes your own consciousness, relies on a deceptively simple but absolutely profound rule: more is different.
So, what exactly does more is different actually mean in this context? Well, it points us directly to the heart of complexity theory. This is the fundamental precept stating that the potential for complexity increases with cardinality. In more rigorous terms, when you assemble sufficiently large numbers of elements, they naturally spawn combinatorial variety. Let's unpack that a bit, because honestly, it is staggering when you really think about it. It's not just that having more building blocks makes a bigger structure. No, it's that as the cardinality, which is just the sheer numerical count of those interacting parts, increases, the number of possible configurations and pathways between them explodes exponentially. You go from simple, straightforward linear relationships to this unimaginable web of combinatorial variety. So a handful of atoms might form a simple molecule. But assemble a few billion of those molecules in very specific structural configurations, and suddenly, you have emergent properties that the individual atoms never, ever possessed on their own. These two concepts, cardinality and combinatorial variety, they're the invisible scaffolding that literally constructs our macroscopic universe from the ground up.
And this brilliantly illustrates that exact point. Take biological organisms, like you and me, and conceptually put them right next to modern computers. Despite being fundamentally distinct in their material substance, right, one being carbon-based organic chemistry and the other being engineered silicon and heavy metals, they both share an incredibly intricate, multi-level logical structure. And this is exactly where complexity theory gets fascinating. When you take massive arrays of basic logical elements, whether those elements are biological cells, complex proteins and neural synapses, or, manufactured transistors and logic gates, they predictably scale up. The combinatorial variety allows these distinct base units to synthesize into highly sophisticated, hierarchical logical structures. Look, a single neuron doesn't think, a single transistor doesn't compute, but string billions of them together in a structured network, more suddenly becomes fundamentally different. You get living beings capable of self-reflection and machines capable of performing trillions of calculations per second.
Section 1. Wheeler's Grand Question.
So as we understand how complexity scales up to create these intricate logical structures, we inevitably have to ask, where does it all fundamentally lead at the cosmic scale? This brings us to the legendary theoretical physicist John Archibald Wheeler. I'm going to slow down the pace here for a second, because Wheeler's perspective requires a profound, honestly mind-bending shift in how we perceive existence itself. Wheeler famously asked this incredible question: will we someday understand time and space and all the other features that distinguish physics and existence itself as the self-generated organs of a self-synthesized information system? Let the absolute gravity of those words sink in for a moment. Why does this matter? Because he's positing that the very substrate of reality isn't just inert matter mechanically bouncing around in a void. He is implying that reality might actually be a self-synthesizing information system. Under this framework, physical laws, space-time, and the particles that inhabit them aren't the foundational hardware of the universe. They are the output. They're the software. Everything we experience, measure, and observe might simply be the emergent phenomena of the universe computing itself, constantly synthesizing vast amounts of underlying quantum information into the reality we actually inhabit.
Section 2. A Unified Reality Theory.
Now, what's really interesting about this slide is that number, 0. Wheeler's insights, his theoretical questions, his mathematical clues, they all act as a massive wake-up call to the scientific community. It's this urgent demand for a unified conceptual model that can seamlessly integrate our thoughts, our observations, and the underlying physical laws. Essentially, we're looking for an entirely new strain of reality theory, one robust enough to handle the sheer computational complexity of a self-synthesizing universe. But despite how profound Wheeler's insights are, when asked how many of the current scientific models successfully respond to all of Wheeler's criteria, the answer is a resounding 0. Not a single prevailing framework in modern physics can fully encapsulate existence as a unified, self-synthesizing information system without making some pretty catastrophic theoretical compromises.
And the reason for that 0 is a terribly frustrating balancing act in modern physics. It's a sort of inherent model compromise. On the one hand, theorists can build models that achieve a small subset of these criteria perfectly. For instance, the Standard Model of Particle Physics. It is astonishingly accurate at describing three of the fundamental forces: electromagnetism, the strong force, and the weak force. It answers those specific physical questions beautifully. But the heavy cost to the remaining criteria is where the entire system breaks down. When physicists force a model to perfectly answer one specific subset of rules, it comes at the steep, prohibitive cost of entirely ignoring the others. The Standard Model, for all its spectacular predictive power, completely ignores gravity. It just cannot account for general relativity. You literally have to give up the macroscopic structure of the cosmos just to accurately describe the subatomic one. There's this inescapable trade-off, where advancing one theoretical front means totally abandoning another.
Section 3. The Physics Divide. Let's move to and see how this builds, because this constant theoretical compromising has led us straight into a brick wall. We're diving headfirst into a grand philosophical and mathematical conflict that is currently holding all of science back. The very foundation of modern physics is essentially split down the middle by a stark dialectic struggle. On one side, we have the thesis, classical physics, culminating in Einstein's general relativity. This is the realm of continuous space-time, right where gravity dictates the smooth, predictable, deterministic movement of stars, planets, and galaxies. But then, on the exact opposite side, we have the antithesis, discrete quantum models. This describes the fundamentally probabilistic, quantized reality of the microscopic world. It's governed by uncertainty principles, wave function collapses, and discrete jumps in energy. So we have continuous geometry on one hand and discrete algebra on the other. They are two totally incompatible mathematical languages trying to describe the exact same universe.
Section 4. The Missing Synthesis.
So the crucial point is this missing synthesis. Here is the great paradox. Virtually everybody in the field acknowledges the correctness of Wheeler's insights about existence operating fundamentally as an information system. We know, both mathematically and intuitively, that he's onto something huge. But the scientific community is completely stuck. We have no unifying synthesis between the classical continuous models and the discrete quantum models because the full depth of the relationship between these two frameworks remains entirely unfathomed. Understanding exactly why this synthesis is so elusive is the crux of the whole problem. First, the higher-order relationships needed to mathematically connect these microscopic and macroscopic worlds are incredibly difficult to pin down. The mathematical formalisms that govern a quark completely break down when applied to the singularity of a black hole and vice versa. Second, answering all the criteria in parallel, finding a framework that perfectly balances quantum mechanics and general relativity at the exact same time without compromising either is logically prohibitive given our current axioms. And finally, we currently lack the integrated, logically tractable concepts to put it all into one big picture. We literally might not have the mathematical vocabulary yet to describe the universe comprehensively as a self-synthesizing system. It's a monumental, perhaps unprecedented puzzle of formal logic and physics combined. Which leaves us right here, staring at the ultimate horizon of modern scientific inquiry. The source material finishes by dropping this massive, provocative question on us. Can this situation be redressed? Can we finally bridge that seemingly insurmountable gap? Find that logical mathematical synthesis, and truly crack the code of reality's information system? Well, there's no neat, easy resolution provided for us today. It's a profound mystery, one that will undoubtedly define the ultimate future of physics and our understanding of existence itself. Thank you so much for joining me on this explainer. Keep wondering, keep questioning, and I will see you on the next one.